A very good evening, all. Welcome to problem solving session number 4 of the course, Mechanics of Materials. So this week, you might have seen topic regarding the strain, the concept of strains, and various topics under strains. So this session, we will see problems based on strain measures and various example problems, which will cover the topic of strain. So let's get started. So first we'll quickly see some of the basic concepts that we require to solve a problem, and then we will see two example problems, which will cover all the categories that you need to solve in a regular assignment. So let's proceed. Yeah. So first, the concept of deformation gradient. Let me write the concepts one by one. First, the concept of deformation gradient. So we know, suppose if we have a particle X in the current configuration, we can map this using a deformation field psi in the reference configuration, capital X comma T. So capital X denotes the reference configuration, portion in the reference configuration. A small x denotes a portion in the current configuration. In this, we can represent the position using some parameter. Parameter is nothing but some psi comma t, right? Suppose if I want to find derivative of this x with respect to this parameter psi, now what will happen? So this is equal to dou psi by dou x times dou x. This is nothing but chain rule that I am using, dou x by dou psi, right? So this particular quantity, again we can represent psi in terms of dou x small x by dou capital X times dou x by dou psi, right? So this particular thing that we call uh, as f. So what is f? F is nothing but a linear function which maps a tangent plane in the current configuration. So this is a tangent, some tangent plane in the current configuration to the tangent plane in the reference configuration, right? So this is the definition of f. It's a linear function which maps a tangent plane in a reference configuration to a tangent plane in the current configuration. Now, suppose if we are given in terms of components, how can we write this f? Let's see. Say, suppose if we have x small x in the current configuration, capital X in the reference configuration. So f will be equal to dou small x by dou capital X, dou small x by dou capital Y. It will have 9 components. Dou small x by dou capital X, dou small y by dou capital X, dou small y by dou capital X, capital Y, dou small y by dou capital Z. And similarly, dou small z by dou capital Z, dou small z by dou capital Y, dou small z by dou capital Z, right? So this is the matrix which contains the 9 components of this deformation gradient, right? Now, let's quickly understand some of the example for finding this. Now, we have a term, suppose if this deformation gradient is a constant throughout a constant matrix, we call that particular case as homogeneous deformation. Homogeneous deformation. Homogeneous deformation means the deformation gradient will be constant, right? The deformation gradient will be constant. Okay. Okay. Suppose if I have say the deformation field given by small x is equal to capital X plus 5 and small y equal to capital Y plus 2. Okay. So in this case, what is the F matrix or deformation gradient? F equal to dou x by dou capital X, dou x by dou capital. This is only two dimension, so I am not including the third dimension. So dou y by dou capital X and dou y by dou capital Y. So this will be equal to 1. What is dou x by dou y? It's 0. And what is dou y by dou x? 0. And what is dou y by dou capital Y? It's 1. So the F is identity matrix. F equal to I. Okay. So for this particular case, F equal to I. So if you want to understand what is this, say suppose if I want to represent this visually, say this is my x coordinate, y coordinate. Initially, my body is somewhere here. What happened? It undergone a rigid body displacement, to some place in the current configuration. So from here to here, right? From here to here. So this is my reference configuration, and this is my current configuration. Okay, fine. So how I am drawing, this is just this particular deformation field. Okay, diagram for this particular deformation field. There is no deformation actually happening. It's only a rigid body displacement, a rigid body translation. I'll write rigid body translation. Okay, there's no deformation. The body is not deforming by itself. If suppose the F matrix is I. Okay, let's take another case. Suppose if your F matrix is like this, you might have already seen this. If your F matrix is cos theta minus sin theta, cos theta, sin theta, and cos theta, you might have seen this last week. Right? This is nothing but transformation matrix. Right? So here it corresponds to rigid body rotation, right? Rigid body rotation. We have seen the x, y, ex, ey basis rotating about z axis in a theta, about angle theta. So this is rigid body rotation. Okay, I'm just giving what is the definition of F, the deformation gradient, and some examples just for you to understand before going into the real problem, the actual problem. Suppose if I want to represent stretching, then let's represent stretching, pure stretching. Actual deformation is coming to the picture. Say for example, if I have a deformation field given by small x equal to 2 times capital X plus 0 0 y, right? And small y is given by 0 0 x plus 1.5 times y. So what happened? It is actually in the x direction, it is stretching double. It's doubling, and in the y direction is going 50%. Okay, which means suppose if I have if this is my x and y, and initially my configuration is, if this is the case, now what happened? In the x direction it is going 2 times, and in the y direction it is going 1 time. Okay, this particular thing is 100%, this is 50%, right? This is 50% stretch, this is 100% stretch. So this is pure stretching. Okay, suppose if I want to write F deformation gradient for this, how it will be? So F is equal to 2, 0, 0, 1.5. See, this is a constant, right? It's a constant. Fine, it's a homogeneous deformation. Okay, and also we can represent another. I can give another example of pure shear. Pure shear Say suppose if I have x is given by x is equal to 1x plus 0.5y and y is given by 0.5x plus 1y. Okay, now how it will become when we plot x and y. When we plot, so suppose initially my body is this. This is the reference configuration. This should be straight. Some body is here. Now after deformation, if it is undergoing pure shear, if you can plot the deformed configuration, it will be something like this. Okay, now for this F matrix, if you want to find, we will have F is equal to 1, 0.5, 0.5 and 1, right? Okay, this is pure shear. And also we can have a general deformation case. General deformation case. There is now not only stretching, not only shear, it's combined. Say x is equal to 1.3x minus 0.375y. Some example I'm giving. Y equal to 2x plus 0.8y. Okay. Now, if I want to find F matrix for this, how will it be? Again, dou x by dou cap x, capital X, dou x by dou capital Y, dou y by dou capital X, dou y by dou capital Y. So here this will become 1.3 minus 0.375 to 0.8. Okay, this is my F. Okay, this is in all the examples that I have showed you, it is constant. F is a constant. Suppose if I have if I want to show you non-homogeneous deformation, non-homogeneous deformation, I can give you an example. Say suppose if you have x is equal to 1.3 xy minus 0.8 y square, y is equal to 2xy plus 0.8 y. Okay. Now what will be f? F will be we have to differentiate x by capital X. So we'll get 1.3 times y, and again x with y, we'll get 1.3x, 1.3x minus 1.6y. Okay, and y we have to differentiate with x, so we'll get 2y. And here, when we differentiate y with capital Y, we'll get 2x plus 0.8. Okay, so this is my F matrix. So here if you can see, all the elements, they are not constants, they have a variable in it, right? So this is non-homogeneous deformation. So what does it mean physically? Physically it means a straight line in the reference configuration becomes a curve in the current configuration. Okay, suppose I have some body here. This is a line, a straight line in the reference configuration. After deformation, that blue color line became a curve. Okay, right? This is non-homogeneous deformation. Fine. Okay, so this is how this is all about the concept of deformation gradient. Basically, this is the main formula that we need so that we can able to find a deformation gradient for any given set of deformation field. Okay, let's move on. The second concept. This is the first concept. So first concept is the deformation gradient. Let me number it. Second main concept is the concept of right Cauchy Cauchy green deformation tensor. So here I am directly writing it's represented by C. So this is nothing but the F transpose times F. Okay, this will come from the derivation like when we derive the quantity F transpose F, we can represent as right Cauchy green deformation tensor. Okay, and the third one is the displacement gradient. Displacement gradient. Gradient of the displacement field. We all know displacement field U is given by small x minus capital X, right? Now, if I want to find the gradient of displacement field with respect to capital X, it will become dou x by dou capital X minus 1, right? I. So this is nothing but F minus I. And this is H. We represent the displacement gradient using the symbol H. Okay, this is the formula for displacement gradient. The relation between displacement gradient and the deformation gradient. Okay, suppose if we are given some displacement field x ux uy uz components is given, then how to find the displacement gradient? Directly, all 9 components we can represent in the matrix form. So dou ux by dou capital X, dou ux by dou capital Y, dou ux by dou capital Z, dou uy by dou capital X, dou uy by dou capital Y, dou uy by dou capital Z, and dou uz by dou capital X, dou uz by dou capital Y, dou uz by dou capital Z. Okay, so this is how we actually compute the displacement gradient. Fine. Now we can write, say, suppose if we have a dx in the current configuration and capital Dx element, a line, small line element in a reference configuration, this we can write as h times dx, right? This, right? So this is a tensor. So we can write this in terms of any tensor we can write in terms of a symmetric and skew symmetric tensor. So H plus H transpose by 2. This is the symmetric part. Dx plus H minus H transpose by 2. This is dx. Okay, this is general representation. Fine. This one, how am I writing? This is coming from the u equal to small x minus capital X. Okay, for a small dx, if I substitute u in terms of h and dx, we can get this. Fine. Okay. Why we are writing? Because this part is we call as linearized strain tensor. Linearized strain tensor. So this tensor has informations about the elongation, the stretching about x, y, z axis as well as a change in angle about of the x and y axis. So we call as linearized strain tensor. Okay, this is the symmetric part, and this we call as infinitesimal rotation tensor. Infinitesimal rotation tensor. Okay. And the next concept that we need is fourth one about stretch ratio. Stretch ratio. Now, what is stress ratio? It's represented by lambda. Say, suppose if I have a direction vector A, I want stretch ratio along that particular vector A. So this is nothing defined as the current length of that particular line divided by the original length or line length in the reference configuration. Okay. REF reference configuration, length in the current configuration divided by length in the reference configuration. If we do all the computations, derivations, we will finally end up in this formula. I am not deriving, you can watch the lectures for detailed derivation. So finally we will get in terms of C, A dotted with A. What is C? C already we have seen, it's nothing but the right Cauchy green deformation tensor, which is F transpose F. Okay. Next is engineering strain. Fifth one is engineering strain. Now, engineering strain is defined as, we all know, the change in length by original length. Epsilon along the direction A is given by L current minus L reference by L reference. So this is nothing but lambda minus 1. Okay. If I want to write in terms of this linearized strain tensor epsilon, this, by the way, this is epsilon. This is epsilon, a tensor quantity, a tensor, right? Second order tensor. Like strain, stress tensor, this is strain tensor. So if you want to write in terms of that, we can write epsilon A dotted with A. Okay, this is A component of epsilon tensor. Fine. And there is a relationship between C and epsilon. Relation between C and epsilon. So we all know C equal to F transpose F. C equal to F transpose F. So F is nothing but 1 plus H the whole transpose. And again F is nothing but 1 I plus HT. Yeah. Now when we multiply this, we'll get I plus H plus H transpose plus H transpose. If suppose if we have a small deformation case, this H is of the order 10 power minus 3. So this H transpose, this particular term, we can simply neglect to 0 for small deformations. Okay, this is an assumption that we are making. So this further we can write using the definition of epsilon. This we can write as 1 plus 2 times epsilon. Okay, so this is a relationship between C and epsilon. Okay, and next concept is angle change. How to find angle change? The formula I'll write directly. So suppose if we have a body basis Ex, Ey and Ez, and suppose if we have a body here, and if there are two line elements, say some A in the direction of A, the direction of B, and if theta is the angle between them, theta reference angle, and suppose if this is now converted in terms of reference configuration, And here, if this is A, this is B, a, small b, and this is theta in the current configuration. Okay. Why I am writing small a, small b? Because that's the current configuration, and capital A, capital B, as usual, is the reference configuration. Here also we can write small a equal to f times capital A. Okay, the f is a second order tensor which maps a line element in the reference configuration to the current configuration. Okay. So now directly I'll write straight away write the angle with angle formula. Cos theta current equal to C A dot B divided by root of C A dotted with A, root of C B dotted with B. Okay, this is the formula. Again, for derivation, you can refer the lectures. And how about the angle change? This is a deformed angle. Theta current is a deformed angle. Deformed angle. Now, if I want to find the change in angle, which is theta current minus theta ref, we say gamma here, gamma between A and B. A and B are two lines. If I want to find the change in angle between those two line elements, so this is given directly by gamma A comma B equal to 2 epsilon A dotted with B divided by sine theta ref. Theta ref is a reference configuration angle. Okay. Yeah. Finally, one more thing. What do we mean by plane strain condition? How do we check that? Okay. We already studied about plane stress condition where we neglect the stresses in the one dimension. We neglect the stresses compared to the other two dimension. Similarly, here we neglect the strain in one dimension compared to the other two dimension. Okay, for example, in case of huge long dams or retaining walls, the strain in one of the dimension where it is dimension is heavier or lengthier, we can assume the strain in that direction is zero. Okay, and this will simplify a 3D analysis into a 2D analysis, and it will help us in solving the problem very easily. So here, what we want to know, how to check whether the condition is plane strain or not. Of course, if we are given with a strain tensor, we can identify, but in general, determinant of this epsilon will be equal to 0 in case of plane strain condition. Okay. So that's it. So all these concepts we will use now to solve the problems. Okay, these formulas are required in order to solve the problems. Right? Let's begin solving the problem. Let me write the question. So the first problem number 1 for today. Suppose if you are given a deformation field is given. It's given by small x equal to capital X, small y equal to 0.2x plus y, and small z equal to capital Z. Okay, this is the deformation field, and a body is given. It's a cube such that x and y and z varies from x, y, z such that -1 centimeter to plus 1 centimeter, all x, y as well as z. This is the question. Okay, this body in the current, reference configuration, all are capital X, capital Y, capital Z, and they have also given for both EX, EY, and EZ represent the basis vectors. The basis vectors same for both the current and as well as reference configuration. Okay, this is given. Now what we have to find? First, we have to find deformation gradient. What is deformation gradient? This is the first question. Okay, now how to find deformation gradient? We just saw the formula for deformation gradient is dou x by dou capital X, dou x by dou capital Y, dou x by dou capital Z, dou y by dou capital X, dou y by dou capital Y, dou y by dou capital Z, dou z by dou capital X, dou z by dou capital Y, dou z by dou capital Z. Okay, this is the formula for deformation gradient. Now let's use this. So when we substitute it here, what will happen? So x is capital X, so it will become 1, 0, 0. And how about y? Y equal to 0.2 plus y, so it will become, for here it's 0.2, here it's 1, here it's 0, and z equal to z, so it will become 0, 0, 1. Okay, so this is deformation gradient f, right? This is part A, that's it. Part B, what they are asking, write Cauchy-Green deformation tensor. B is write Cauchy-Green deformation tensor. Now how to find this? Once if we have F tensor, this is easy. C is equal to F transpose F, right? Directly we can just multiply. So this is equal to F transpose 1, 0, 0. So it's transpose. So 1 to 0, 0, 1, 0, 0, 0, 1 times 1, 0, 0, 0 0.210 This is equal to, again we have to multiply 1 plus, just a minute, yeah. So 1 plus 0.04 is 1.04, and first row second column 0 plus 0.2. Now I think let's do this in, try to do this in MATLAB. I'll also write the code directly so you will know. There is an online version available, so you can just try to log in and sign in, you create your account, or if you have in your computer also you can do. So what we want to do, we want to multiply two matrices. So my F matrix is given by 1, 0.2, 0, first row, 0, 1, and 0, and 0, 0, 1. Okay, so this is my F matrix. And C, I want F transpose F times F. Okay, so here I'm getting the answer. So C I'm getting is 1. 1 second. I'm not getting 1.04 in the computer. I'm just thinking, is there any error? Because first row and first column, 1 into 1 plus zero point 0.2 into zero point 0.2 plus 0. So F transpose. Oh, I guess I have written it wrongly. Yeah, now I will get. Yeah, it's correct. So I'm getting 0 0.2, 0, 0 0.2, 1, 0, 0, 0, 1. Right? That's it. So this is my C, right Cauchy green deformation tensor. Okay. So third question, they are asking what is the displacement gradient? Uh, Part C, displacement gradient. Now, displacement gradient is given by, we saw, what is displacement gradient? What is the relation between displacement gradient and deformation gradient? Yeah, displacement gradient H is equal to F minus I. So directly H is equal to F minus I. Okay. So this is equal to let's do this here. H is equal to F minus identity of 3. Okay, identity of E by E3 will create a 3 by 3 identity matrix. So this will give us 0, 0, the second 0, 0.2, and rest of the things are 0. Okay. And fourth question, part D, we have to find the linearized strain tensor. Fine. Linearized strain tensor, we saw epsilon is equal to half H plus H transpose, right? So this is equal to, again, let's go there and directly code. So epsilon, I can create a variable equal to half times. So this is just a calculator. I'm using it as a calculator. H plus H transpose. How much I'm getting? Epsilon as 0, 0 0.1, and 0 0.1. 0, 0, 0, 0, 0, 0. Okay, that's it. So here epsilon xx is 0, which means along x direction the strain is 0, along y direction strain is 0, z direction strain is 0. but there is epsilon xy component 0.1. Fine. There is an angle change in it. Fine. So this is the linearized strain tensor. And fifth subdivision, they are asking stretch ratio. So we have to find the stretch ratio of a line initially oriented along EY direction of length 1 mm located at some point, 0.5, say 0.5 comma 0.5 comma 0.5 in the reference configuration. uh, they have asked us to use C, okay, the right Cauchy-Green deformation tensor. Fine. So how to find the stretch ratio? So we have already seen this formula. Lambda in the direction of A equal to root of C times CA dotted with A. Okay. Yeah. CA dotted with A. Now, first we have to find what is CA, and we have to do the dot product of C and A. So C is 1.04, 0.20, 1.04, 0.20, and 0.210 and 001 times A. A is what? In this question, A is along EY direction they have given. So A will be 0, 1, 0. So vector. Okay. So this will be equal to 0.210. Fine. When you multiply. And now we have to do this dot product CA dotted with A will be 0.210 dotted with 010. So this is nothing but 1. Okay, this rich ratio we are getting in the direction of EA is equal to 1. Fine. Now, the next part of the question, same question, stretch ratio of a line initially oriented along not EY direction, but instead of EY, the difference here is EX plus EY by root 2 direction. No direction. Okay, this is the only change. Okay, nothing else is changed, so we have to repeat the same thing. So C will be equal to, again, not C times A. C times A will be equal to 1.04, 0.20, 0.210, 001 times 1 by root 2, 1 by root 2, 0. So this will become, we need calculator. Let's use MATLAB. So C already have here. Let me define a vector A is equal to 1 by square root of 2, again 1 by square root of 2 time, and one more 0. Now C times A is nothing but 0.8768.8485 and 0. Okay, now we have to do the dot product. CA dotted with A is 0.8768.8485 dotted with 1 by root 2, 1 by root 2, 0. This times this is nothing but 1 by root 2 times 0.8768 plus 0.8485, right? So here again, let's go back here. So what is this? This is stretch ratio, right? Stretch ratio equal to dot. Here we do dot product using the command dot. First vector is CA, second vector is CA. That's it. Done. So this will give us the answer directly. So it is 1.22. Okay, this is stretch ratio. The change stress ratio actual formula is the current length in the current configuration divided by length in the reference configuration. Okay, that is 1.22. So in the current configuration, the line has expanded. Okay, it became 22% more than the initial. And next part of the question, part G, we have to find the engineering strain of the line. Find the engineering strain of a line initially oriented along EY direction of length 1 mm located at 0 comma 0.5 comma 0.5. Actually, since it's a homogeneous deformation, it's not a function of xyz. So anyhow, this point we are not using. Okay, and they have asked us to use epsilon. Okay, we have to find using epsilon. Now, how to find engineering strain? What is the relation? Engineering strain is given by epsilon A dotted with A. Okay. So here what is our A? EY. EY is our A. So A will be A is equal to 0, 1, 0. Before that, let's write the formula for that. In engineering strain, epsilon of A equal to epsilon tensor A dotted with A. Okay. A will be 0, 1, 0. Fine. So when we go back and substitute, this will become epsilon of A is equal to, what is the epsilon's tensor? 0, 0.1. Only two components are non-zeros. Remaining everything is 0 times 0, 1, 0 dotted with 0 and 0. First we have to multiply these two. So it will become 0.1, 0, 0 dotted with 0, 1, 0. Nothing but 0. Okay. So the engineering strain along EY direction is 0. Next question, part H. Part H, same, but they have changed the direction along EX plus EY 1 by root 2. Okay. So here A will become 1 by root 2, 1 by root 2, 0. This is the only change. So epsilon of A will be again 0, 0.1, 0, 0.1, 0, 0, 0, 0, 0, 1 by root 2, 1 by root 2, 0, dotted with 1 by root 2, 1 by root 2, 0. Fine. So let's again do this here. So this is engineering strain. We can write any variable as a representation. So engineering strain is equal to epsilon. Epsilon is there already times A, epsilon times A dotted with A. So this dot product, okay, A is already there. So I am just writing directly. So this will give us 0.1. Okay. When you do multiplication, you will get 0.1. That's it. Fine. So yeah, this is over. Let's move on to the next subdivision. The next subdivision, they are asking us to find subdivision number HI. What is the deformed angle between two line elements? Find the deformed angle between two line elements along EX and EY direction at point 0 comma 0.5 comma 0.5. Okay, using C, right Cauchy green deformation dash, because yeah, we can use C. Also we can use that epsilon, right? For small deformation we have a formula, a short formula which will compute. So here particularly they are asking us to use a right Cauchy green deformation tensor. So again we have the formula. So the formula for reformed angle is C A dotted with B divided by root of C A dotted with A times root of C B dotted with B. Let's use that. So when we use, it will become, let's write the formula first. Deformed angle that is theta in the current. So it's cos, okay, theta in the current is equal to cos inverse of C A dotted with B divided by root of C A dotted with A root of C B dotted with B. Okay, correct? So this is the formula. Yeah. Let's move forward. So A is EX. So EX means A will be 1, 0, 0. Okay. Now, let's compute each of the quantity one by one. CA dotted with B. This is equal to C is 1.04, 0.2, 1.04, 0.2, 0.2, 1, 1, right? Hope this is right. 1.0 to 0.2. YY is and ZZ is 1. Correct. 1.4, 0.2, 1. Yeah. So A is 100 dotted with B is, yeah, B we have to write because they have given, right, deformed angle between two line elements. So one of them is A, another one is B, 0, 1, 0. So here when we multiply, we will get 1.04, 0.2, 0. Okay, dotted with 0, 1, 0. So this will give us 0.2. Okay, this is the numerator. The denominator will become C A dotted with A 1.04, 0.2, 0, 0.2, 1, 0, 0, 0, 1. A is 100 dotted with 100. Okay. So this actually will give us this element. So let's again multiply. So 1.04. This is 100. So it will give us the first column. Okay. Dotted with 100. In this again, see, it will give us 1.04. Fine. And how about C, B dotted with B? 1.04, 0.2, 0, 0.2, 1, 0, 0, 0, 1 times 0, 1, 0 dotted with 0, 1, 0. Now this will give us the YY, right? This element. So 0, 1, 0 means second column. So second column is 100 dotted with 0, 1, 0. Okay, so this is 1, right? Now we have everything. Let's substitute everything into the formula. So theta current will be equal to cos inverse of CA dotted with B. CA dotted with B is 0.2 by square root of 1.04 and square root of 1. We need calculator. So let's do a normal calculator. So square root of 1.04, 0.2 divided by square root of 1.04. I'll run this in command. It is cos inverse of 0.1961. So again we have to convert this. Cos inverse is a cos of this. This is theta current. So it is in radians. So 1.3734 radians. We want in terms of degrees. So into 180 by pi. Okay, so this is equal to we are getting 78.69 degrees. Okay, 78.69 degrees. This is theta correct. Fine. That's it. The next part of the question, IJ, same question, but here we have to find the angle, deformed angle between not EX and EY. Instead of EX and EY, we have to find between EX and EX plus EY by root 2. Okay, so same process we have to repeat. So instead of 100, we have to 010, we have to substitute 1 by root 2, 1 by root 2, 0. Okay, now let's do this using MATLAB directly instead of doing step by step. Okay, so the formula for theta current is cos inverse of C times A times B. Okay. By the way, this has to be a dot product. So dot of CA dot B and divided by, this is numerator done. Denominator is, first in denominator is square root of, again dot CA dotted with A times square root of CA comma, sorry, CB comma B. Okay, that's it. So this will give us in degrees, sorry, in radians, this into 180 divided by pi. Okay, so we have to define what is A, what is B here. A is the question 100 EX, right? So 100, it's a vector. So vector will put semicolon. Okay, so it will become a 3 by 1 vector, and B is 1 by root 2, 1 by root 2 and 0. Okay, so this is A, this is B. Let's run to find theta in the current configuration. Okay, there is an error. Too many input arguments. There is some syntax wrong. Let's see what it is. Dot. Okay, here I forgot to give dot, right? Square root of one dot will come. One more bracket should come. Okay, so let's check it once again. Cos inverse of dot of CA and B divided by, or to avoid this, let's write numerator, denominator separately. Okay. Let's define numerator and denominator separately, so it is easy. So denominator equal to, what is denominator? Square root of CA dotted with A times square root of, yeah, there's one extra, CB comma B. Yeah, this is extra. Here one bracket. Okay. So this is denominator. Similarly, numerator will become C A comma B dot product of C A and B. Okay, this is done. Numerator divided by denominator into 180 by pi. Fine. I hope it is right. There should not be any error now. Let's run 38.8845 degrees. Okay. So here, what was our A? A was A was 100. B was 1 by root 2, 1 by root 2, 0. And theta in the current configuration was cos inverse of CA dot with B by square root of CA dot with A square root of CB dot with B. So this turned out to be 38 degrees, right? 38.88 degrees. Right? That's it. This is theta in the current configuration. Okay. Next subdivision. Last few more subdivision to go. The last variety. So I J K subdivision. So we have to find the change in angle. Change in angle between two line elements initially oriented along X and EY directions. At 0, 0.5, 0.5 using the definition of epsilon, okay, is dash. Fine. So how will we find a change in angle? Change in angle is epsilon equal to gamma equal to epsilon A dotted with B divided by sine theta ref, right? We have seen this 2 times epsilon A dot with B times sine theta ref. Let's use that formula. Now, what is A, what is B in this question? A is 100, B is 010, because A is EX and B is EY. Okay. Now, what is theta ref? Theta ref. How will we find theta ref? Same, using the definition of dot product, we can find cos inverse of A dot with B divided by mod A mod B. Right. So mod A mod B is 1 1. So A dot with B is 0. Cos inverse of 0 is 90 degree, pi by 2 or 90 degree. Okay. So sine theta will become 1. Okay. A denominator will become 1. That implies gamma is nothing but 2 epsilon A dotted with B only for this problem. So let's multiply 2 times epsilon tensor is Okay, 0.1, 0.1, rest of the things are 0. 0.1, 0.1, 0, 0, 0, 0, 0, 0 times 1, 0, 0 times 0, 1, 0. Let's multiply. This is equal to 2. First column we will get dotted with 0, 1, 0. Nothing but 2 into zero point 0.1 into 1, which is 0.2. Okay. So this is 0.2. Just a second. Let me check. Okay. What I was thinking whether this point 2 was in degrees or in radians. How we derive this formula? We derive this formula by assuming um, gamma to be small, right? So we didn't make any assumption to directly convert it into degree. So it should be in radians. So if you want to convert in terms of degrees, again zero point 0.2 into 180 by pi. This will give us zero point 0.2 into 180 by pi. It's 11 point. Okay, fine. Next question, same question, but we need to find along two different vectors. The vectors is given by Ex and Ex plus E as usual. Okay. Question subdivision KL, same question but along Ex and Ex plus Ey by root 2. Okay. Now, how will we solve? Same, right? A is 1, 0, 0. B is 1 by root 2, 1 by root 2, 0. Now, I think let's use MATLAB. Oh, okay. Let's use MATLAB for this. So we have to find epsilon, it's gamma. So gamma equal to 2 epsilon A dotted with B by sine theta ref. So first of all, we have to find theta ref, and then we have to see calculate. So let's find theta ref. Theta ref is equal to, what is the formula for theta ref? Theta ref equal to A cos inverse of dot of A and B divided by nor of A and nor of B. Okay. There should be a bracket here. The denominator is a common. Okay. So this is theta f. By the way, what is A and B? I think already it is there. A is 1 by root 2, 1 by root 2 0, and B is no, for this particular problem, A is 1 0 0, and B is 1 by square root of 2, 1 by square root of 2, and 0. Okay, so A and B. And theta ref is equal to, again, dot product of, yeah, I think let's find. Is there any error? 1 by square root of 2? Yeah, correct. There should be a semicolon, because otherwise it will detect as non-consistent dimension. So again, this is in radian, this into 180 by pi. So 45 degrees, right? Yeah, of course, it's 1 by root 2. So cos 45 sine 45. So theta ref equal to 45 degrees. So sine theta ref will be 1 by root 2. Okay. Now the remaining things we have to solve. 2 times epsilon. 2 times epsilon is 0, 0.1, 0.1, 0, 0.1, 0.1, 0, 0, 0, 0, 0, 0. A dotted with B. A is 1, 0, 0. Dotted with 1 by root 2, 1 by root 2, 0. Okay, so this is equal to 2 will be there, and 0, 0 0.1, first column, dotted with 1 by root 2, 1 by root 2, 0. So this will be 2 times 0.1 into 1 by root 2. Root 2 will get cancelled. So thing is 1.414, 0.1414, right? Okay, this is gamma AB. Okay, if you want to convert in terms of degree, this multiplied by into 180 by pi. Okay, I think this is what is there. 0.14, I'm just using this 0.1414 into 180 by pi. 8.1 degrees. Okay, that's it. Fine. And next question, deformed shape of the circle. Part subdivision part L, M, deformed shape of a circle given by z is equal to 0 and x square plus y square is equal to 0.01. Okay, this is given, a circle is given in the reference configuration. What will be its shape in the current configuration? That's the question they are asking. So as usual, let's substitute the capital X, the deformation field. So capital X is nothing but small x. So this is fine, and capital Y is small y minus 0.2. This is from the question, and again capital Z, small z is equal to capital Z. Okay, Now let's substitute all these. So x square plus, instead of capital Y, I'm substituting my y minus 0.2x, the whole square is equal to 0.01. So this is equal to x square plus y square plus 0.04 x square minus 0.4 xy is equal to 0.01. Okay, 1.04 x square plus y square minus 0.4 xy minus 0.01 equal to 0. Okay, so now this looks like an equation of conic, right? Where it is ax square plus bxy plus cy square plus dx plus ey plus f equal to 0. Now here if b square minus 4ac equal to 0 means it's a parabola. If it is negative means it is ellipse. If it is b square minus 4ac is greater than 0 means it's hyperbola. Okay, so what is b square minus 4ac? For our case, a is equal to 1.04, b is equal to minus 0.4, c equal to 1. Therefore, the delta is equal to minus 0.4. Okay, this is delta discriminant. 0.4 square minus 4 times 1.04 times. So this will be 0.4 square minus minus 4 into 1.04. This is a negative. Yeah, of course, it's a negative, and hence it is ellipse. Okay, so the deformed shape would be an ellipse. Fine. And last question, is this a small deformation? Subdivision n. Is this a small deformation? How to find? If suppose if h is of the order 10 power minus 3, we say it is a small deformation. Order of h, the displacement gradient, should be of 10 power minus 3 or lesser, right? So if that is the case, it is small deformation. But in our case, what is h? Where is h? Yeah. No, it is. Sorry, I have to change the screen. So I'm sorry, I'm not changing the screen here. Yeah. In our case, h is not of the order 10 power minus 3. It is of the order 10 power minus 1 only. So it is not a small deformation problem. Okay. So answer is no. Since order of h is only 10 power minus 1. Okay. Fine. So this completes the first question fully. Fine. Let's move on to the second question. Last question for today. Problem number 2. Same, some of the part will repeat, but the given is different. What is given in the question is, instead of a deformation field, we have been given with a displacement field. Ux is equal to 0, uy is equal to say y plus z 10 power minus 4, and uz is equal to y minus z, again 10 power minus 4. Okay, this is given. And again, we have to find the displacement gradient, deformation gradient, a linear strain tensor, engineering strain, change in angle, and so on. Fine. Let's do one by one. First, let's find what is displacement gradient. How will we find the displacement gradient? So h is equal to, so since the displacement vector components is given, so let's directly write ux by capital X, ux by capital Y, ux by capital Z, and uy by capital X, uy by capital Y, uy by capital Z, and uz by capital X, uz by capital Y, uc by capital Z. Okay, so this is H matrix, displacement gradient tensor. So ux is 0, so first row everything will be 0. Uy, when we differentiate with the x, it is 0, and when we differentiate with y, it is 10 power minus 4. When we differentiate with z, it is again 10 power minus 4. This is 0, this is 10 power minus 4, this is minus 10 power minus 4. Okay, simply we can write this 10 power minus 4 outside, so that it will be 0, 0, 0, 0, 1, 1, 0, 1, minus 1. Fine. So this is H matrix for us. Now, second question, ask us to find what is the deformation gradient. Deformation gradient. How to find deformation gradient if H is given? What is the relation between H and F? We saw at the beginning of the session, today's session. H is equal to F minus I. So F equal to H plus I, right? So F equal to H plus I. Right? This is F. So this implies F is equal to, what is H? 10 power minus 4, 0, 0, 0, 0, 1, 1, 0, 1 minus 1 plus 1, 0, 0, 0, 1, 0, 0, 0, 1. So this will be 1, 0, 0, 0, 1 plus 0 0.00, 2, 3, 4, right? 1, 2, 3, 4. No. 1, 0 is, yeah. And again 0.0001, 10 power minus 4, and 0.0001, and 1 minus is 0.9999. Okay, so this is F. Next question, we have to find for part C, linearized strain tensor. How to find linear strain tensor? Again, the relationship we know, epsilon is equal to half H plus H transpose. Fine. So this is equal to half H is, yeah, 10 power minus 4. Only these 4 will be 1. 0, 0, 0, 0, 1, 1, 0, 1, 1. This is H plus transpose of H will be 0, 0, 0, 0, 1, 1, same 0, 1, 1, symmetric. So this will be half into minus 4, 0, 0, 0, 0, 2, 2, 0, 2, 2. Okay. So again 10 power minus 4, 0, 0, 0, 0, 1, 1, 0, 1, 1. Okay. So this is C, subdivision D. We have to find engineering strain of a line initially oriented along EZ direction of length 1 mm located at 0, 0.5, 0.5 coordinate computed using linearized strain tensor. Strain tensor. This into 10 power minus 5. Okay. So we have to find engineering strain. So what is the formula for engineering strain? Epsilon of A will be epsilon A dotted with A, right? What is A in this problem? A in this problem is 0, 0, 1, easy direction. Okay, this is given. So A will be 0, 1, 0. So this implies epsilon of A will be, this is epsilon 10 power minus 4, 0, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 1, 0, 0, 1. Okay, so this is nothing but ZZ component, right? So just 10 power minus 4. Okay, but we want to write in terms of 10 power minus 5. So what I'll write? I'll write point uh, 10 into 10 power minus 1 into 10 power minus 4, which is 10 into 10 power minus 5. Okay, so the answer is 10. Next subdivision. Subdivision E, we are asked to find the same question but along EZ plus EY divided by root 2. Okay, so let's do epsilon of A is equal to 10 power minus 4, 0, 0, 0, 0, 1, 1, 0, 1, 1 times 0, 1 by root 2, 1 by root 2 dotted with 0, 1 by root 2, 1 by root 2. Okay. So when you multiply, what it will become? 10 power minus 4 outside. So first row, first column entirely 0. Second row, second column 1 by root 2 plus 1 by root 2 is 2 by root 2, which is 2 by root 2 is nothing but root 2. In third row, again it is root 2 dotted with 0, 1 by root 2, 1 by root 2. So this will give us 10 power minus 4, 1 by root 2 times root 2 is 1 plus 1 is 2. Okay, 2 into 10 power minus 4. Again, if I want to write 20 into 10 power minus 5. Okay, so the answer will be 20. Fine. This is part E. Next part F. We have to find the change in angle. Change in angle between two line segments. Initially, let me write elements. Initially oriented along EY and EZ direction at 0, 0.5, 0.5. Okay, computed using epsilon, because here it is possible degrees. Okay, change in angle. Since it's a small deformation, for this problem we can confidently use the epsilon. Okay, epsilon A comma B. So the last problem, although we used, it won't be much accurate, because last problem number 1 was not a small deformation problem, it's a large deformation problem. So we cannot make that assumption. Actually, in the derivation of this gamma, we would have used assumption that the gamma angle is less than very small. Okay, so but for this problem we can confidently use, what is that formula? 2 epsilon A dotted with B divided by sine theta ref. Okay, so in this problem, theta ref is again along what is A and B, by the way. A equal to 0, 1, 0 and B is equal to 0, 0, 1. Okay, so sine theta ref is 1, because they both are mutually perpendicular. So angle between them is 90 degrees. So sine of 90 will be 1. And let's multiply 2 epsilon A dotted with B is equal to 2 times epsilon was 10 per, yeah, 0, 0, 0, 0, 1, 1, 0, 1, 1 into 10 per minus 4 times 0, 1, 0 dotted with 0, 0, 1. So this should give us the YZ component of this tensor. Where is the YZ component? Here. So that is 1. So 2 into 10 per minus 4 into 1. Right. So again we want in terms of 10 per minus 4 degrees. So this will be 2 into 10 per minus 4. Okay. That's it. And F, okay. The next question, does this deformation lead to plane strain? Subdivision G, does this deformation leads to plane strain? So what is the condition we have? Determinant of epsilon is equal to 0. Of course, here determinant of epsilon is 0. So it is a plane strain condition. Yes, it is a plane strain condition. Fine, because the determinant of epsilon is 0. One row or one column 0 means the determinant will be 0. And finally, we have to find what is the deformed shape of circle x equal to 0, y square plus z square equal to 0.01. Okay, so for this we need the deformation field, but in the question only displacement field was given. We have to find the deformation field and then we have to substitute. So what was given in the question? ux which is x minus capital X is equal to 0, which is small x equal to capital X, uy which is equal to uh, small y minus capital Y is equal to capital Y plus Z into 10 power minus 4. This was given in the question. So small y will be capital Y plus capital Z into 10 power minus 4. And uz is equal to small z minus capital Z. This is equal to capital Y minus capital Z 10 power minus 4. So small z equal to capital Z plus y minus z 10 power minus 4. Okay, fine. So let's substitute. Okay, we need capital Y, capital Z in terms of small y, small z. So we need to do the other thing, right? So let's say this is 1, this is 2, this is 3. So equation 2 implies y is common. So 1 plus 10 to the power minus 4 plus z 10 to the power minus 4 is equal to small y. Let's substitute z equal to y minus capital Y into 1 plus 10 to the power minus 4 times 10 to the power minus 4. Substitute this is 4 in 3 implies small z equal to y minus capital Y into 1 plus 10 to the power minus 4 divided by 10 to the power minus 4 plus capital Y minus, again I don't have space, so let me write it down, y minus small y minus capital Y into 1 plus 10 to the power minus 4 divided by 10 to the power minus 4 the whole times 10 to the power minus 4. Okay, so this implies small z equal to y minus capital Y into 1.0001 divided by 10 to the power minus 4 plus 10 to the power minus 4y and minus y minus y into 1.0001. Okay, this denominator will go. So what we want? We want actually by the way, let's do this in terms of let me do this in terms of uh, matrix so that it is very easy for us. Instead of writing all these equations, we can use the concept of the deformation gradient. So let me write those three equations: small x equal to capital X and small y equal to small y is equal to cap 1.0001 capital Y plus 10 power minus 4 capital Z, right? Yeah. And small z equal to uh, 1.0001 capital Y, and 1 minus z is 0.9999 capital Z. Okay, now I can write this as xyz equal to 1 0 0 0 1.0001 and 0.0001 and 0 1.0001 and 0.9999 times capital X, capital Y, capital Z, right? So what we want to capital X, capital Y, capital Z, this will become inverse of 100. So now I'll use some calculator so that my problem will be solved easily. Instead of solving those equations, this is an elegant and easy way. Inverse of small x, small y, small z. What is this? Inverse of this what? Let's go with MATLAB. Let's define a matrix. Some matrix name is say F1 is equal to 1 0 0 0 0.0 sorry 1.0001 0.0001 0 1.0001 0.9999. Okay, this is some matrix. So what I want, the inverse of F1. So inverse of this matrix is 1 0 0 0 1. I am noting it down 0.0001 0 minus 1.0002 and 1.0002. Okay, so this x, y, and z. That's it. Let me come back to the screen. X, y, capital Z. So now we got it right. So capital X equal to small x, capital Y equal to small y minus 0.0001 y. So z, capital Z equal to minus 1.0002 y plus 1.0002 z. Okay. Now what we have to find, the question is deformed shape of the circle, y square plus z square equal to 0.01. So y square plus z square equal to 0.01. So when you substitute y minus 0.0001 z the whole square plus 1.0002 z minus 1.0002 y the whole square equals 0.01. So y square plus this is 0.0001. So this is 10 power 1, 2, 3, 4 minus 4. So you will get 10 power minus 8 z square, a square plus b square minus 2ab. So minus 0.0002 yz Similarly, here 1.002 I would have taken common. So 1.0002 square z minus y the whole square only will be there. So plus 1.0002 the whole square z square plus y square minus 2zy equal to 0.01. So when we further simplify this, let's go to MATLAB. 1 plus, so 1 plus 1.002, 1 plus 1.0002 whole square. So 2.0004y square, and z is 10 to the power minus 8 plus 1.0002 the whole square. It's again 1.0004. Yeah, we could have neglected this 10 power minus 8 term. Okay, this plus this, and lastly we have minus 0.0002 yz minus 2 times 1.0002 square. Okay, so this gives us minus 2.001 yz. Okay, apart from that, we have minus 0.01 coming from the right side. Okay, so finally we somehow arrive at the equation of conic. Now let's, this is A equal to 2.0004, B equal to minus 2.001, C equal to 1.0004. So B square minus 4AC, if we check, minus 2.001 square minus 4 into A into C, 1.0004. We'll get negative. So it's less than 0. Hence, we say it is an ellipse. Therefore, the deformed shape is an ellipse. Okay, that's it. Fine. So with this, I think we come to the end of the problem solving session. So let me quickly recap whatever we have seen today. First, we started with the concepts required, the formulas required to solve the problem of week 4 assignment. So first is deformation gradient. We saw deformation gradient as a linear function which maps a directed line segment in the reference from the reference configuration to the current configuration, right? And we saw for homogeneous deformation, the F matrix should be constant. Then we saw what do we mean by right Cauchy-Green deformation tensor, which is C equal to F transpose F. Then we saw the displacement gradient. H is given by F minus I, right? The gradient of the displacement. Then the stretch ratio, this is the current length by the original length, the ratio. And engineering strain, the change in length by the original length, which is given by epsilon A dotted with A. Fine. Also, we saw the formula for angle change. Okay, the deformed angle as well as the change in angle for small deformation case. Finally, we saw the plane strain condition, which is determinant of epsilon is equal to 0. Oh, okay. Okay. There is a small Okay, fine. There is a small correction in one of the problem that I have given in the final step. So for this problem in part F, we found the change in angle between A and B, but at last it was in radians, right? But in the question they were asking us in degrees. So this we have to convert this into degrees. So this you just multiply by 180 by pi, so we'll get 114.5916 into 10 power minus 4 radians, degrees. Okay. Just please make a note. The final answer has to be in degrees. So if you're, but this formula, calculator, everything will give us in radians. So we have to convert the radians into degrees, right? Here I forgot to tell you. Sorry for that. Okay. Fine. So with this, we'll stop for today. We'll see the next week's problem in the next Friday, 6 to 8 p.m. Thank you. Thank you very much, everyone. Thank you.